Hello everyone, welcome. Today we are having Yuji Tachikawa from Kauli IPMU, and he's going to tell us about global anomalies of heterotic string theories. Over to you, Yuji.
Okay, thank you very much. It's an honor to give this seminar. In fact, this is my first Zoom seminar ever since the pandemic started. That's because whenever I get asked to give a seminar, either it is in the wrong time zone, or I always have a younger collaborator, so I always suggested the organizers to give them the chance to present the work. But somehow last March, I decided to write a single authored paper, and time zone difference between India and here are not that big. So it's really an honor to give this my first ever Zoom seminar. Of course, I've given Zoom lectures to the students, but yeah, it's really nice to be able to do this. So the topic today is on global anomalies of heterotic string theories. And so let me start with a casual introduction. String theorists often say string theory is miraculously free of inconsistency, right? And some of us often say string theory is the only consistent theory of quantum gravity. Are you really sure? That's my question. Really? Really? That's my question to all of you. And today I'd like to discuss global anomalies of perturbative heterotic string theories, which sounds very esoteric, honestly speaking. But no, one of my points today is to convince you that this is not such an esoteric question. It's a very basic question. That's what I'd like to convince you. So before talking about heterotic strings, let's remind ourselves the prototypical example of global anomalies, which is the SU2 anomaly of Witten. So what happens is that in 4 dimensions, there is a non-trivial large gauge transformation associated to a non-trivial homotopy group, pi4, of the gauge group SU2, which happens to be Z2, right? So you can try to perform this global gauge transformation on the 4-dimensional spacetime, and the Fermion path integral measure can pick up a non-trivial phase under it. So for example, if you have n doublets of Weyl fermions, that produces a phase which is -1 to the power n2, right? So if you have odd number of doublet fermions, then the theory is inconsistent. You cannot gauge SU2. More generally, if you have, if we denote by nk the number of Weyl fermions in the k-dimensional irreducible representation of SU2, the ones which contribute to this type of anomaly is the 2-dimensional one, 6-dimensional one, 10-dimensional one, etc. So this is the formula for the global anomaly, right? So let's now ask the following question. Is Witten's SU2 anomaly absent in 4D heterotic compactifications? We often say that string theory is automatically consistent, right? So I assume that this has been answered, but in fact it's not. It's an open question. So let's try to think about it. So the worldsheet theory of this heterotic string consists of the following ingredients. So the ghost and super ghost contribute -26 and -15 to the central charge. And the non-compact part of the spacetime, which is assumed to be 4-dimensional, gives you 4 scalars and 4 fermions, which contributes to 4 to CL and 6 to CR. Therefore, to cancel the central charge, the internal CFT needs to have this particular central charge, 22 and 9, right? And my convention is that in the heterotic worldsheet, the left movers are non-supersymmetric and the right movers are supersymmetric. That's just a convention. So how can we compute this anomaly in heterotic strings? You might think that it might involve tons of esoteric mathematics, right? But of course, that's not the case, because if you are a string theorist, you know how to compute space-time spectrum given a worldsheet CFT. So you just apply that textbook material to count the number of doublet fermions in the system, and you just check whether it's odd, right? So let's remind ourselves the basics of perturbative heterotic strings. So in order to get fermions, you need to consider the R sector, right? I mean, in the case of type 2, you need to consider R and S sector, but here it's heterotic string, so we just consider the R sector. So the right movers, which are supersymmetric, are put into the R sector. Where do the massless fermions come? Well, they are those with L0 and L0 bar being 1 and 0, right? I mean, the right movers are supersymmetric, and it's put on the R sector. So you just have to consider the lowest mode, which is 0, which has energy 0. On the left moving side, it's basically equal to the bosonic string. Therefore, in order to get the lowest mode, you need to use L0 equals 1. And finally, you need to get the counting of the chiral modes, but the space-time chirality is correlated with the chirality of the internal CFT. Sorry, the fermion number of the internal CFT, thanks to the standard GSO projection. So that's how it goes. So we can translate the question of the SU2 anomaly of 4D compactification of heterostrings into a purely CFT question. So the question becomes the following. Let's take an SU2 symmetric 0, 1 supersymmetric SCFT in 2 dimensions with this particular central charge, 22 and 9, right? Now you decompose the Hilbert space of this CFT, and you just pick the Hilbert space with L0, L0 bar being 1 and 0 in the R sector, right? You just pick basically the lowest state, the lowest states. And you decompose it into SU2 representation, which is possible because we assume that it is SU2 symmetric to produce SU2 gauge symmetry. Then the question is whether this number is +1. Otherwise, this heterotic compactification is inconsistent because you cannot gauge the SU2 gauge field on the uncompactified 4-dimensional side. So that's the issue, which is a non-trivial question. And I don't know how to address this using our standard toolkit we learn in our field. So I learned the existence of this question from this paper, Enoki, Sato, Watari, which appeared May last year. So they are all my colleagues here in IPMU. Watari is the faculty member, and Enoki and Sato are his 2 students. And in fact, I learned the question before they published this paper. In fact, it was during the almost last tea time in IPMU before the pandemic started. So they told me about their recent progress in understanding it. So they realized that there is this particular question, which is unanswered, and they assumed more space-time supersymmetry with n equals 2, right? So n equals 2 heterotic compactifications down to 4 dimensions is a very popular subject and lots of literature. So you can study a lot. So they could show that the Witten anomaly doesn't appear in many cases, many classes of compactifications, but they couldn't find a general proof. So that's the situation. And my point today is that somehow the mathematical theory of something called topological modular forms can address this question, assuming, again, a certain conjecture under the name of Segal-Stolz-Teichner conjecture. And this TMF is esoteric subject, I'm afraid. I mean, the question itself of this heterotic anomaly is, I think, a very fundamental one. But the way I propose to solve this question is admittedly rather esoteric. But there are a couple of papers on TMF on our physics side, but that's not very long. in fact, this is the exhaustive list. Usually in our field, it is not possible to give you an exhaustive list of papers on a particular subject, but this is really the exhaustive list of papers on TMF. And so it's either written by Guyot and Johnson, Fried and plus Witten, or by Kufoff, Vafa. And I just wrote a paper on March. So this is a young field where newcomers are welcomed. So during this talk, I just want to sell the concept of TMF and how it can be used to solve this question. Yeah, and these references, I will give you the link to these slides later, so you don't have to worry about the precise references. You can just download the slides and just click the links.
Yuji, one question.
Yes, please.
So if you were to find a CFT, let's say, just where this does not work, what would that say about the string theory?
Well, so if there is such a CFT with odd number of doublet, then that means that the framework of heterotic string theory is not in itself automatically consistent. So you need to add some additional constraint, right? So it's like having three possibilities in 10-dimensional superstring theory, in heterotic string theory, right? And there can be three types of gauge group, but somehow you need to choose the anomaly canceling one by hand, right? But that's not the case in 10 dimensions. Automatically, what we know is that in 10 dimensions, you need to have, on the bosonic side, C equals 16 additional sector, right? And because of the modular invariance, we are forced to take either E8 times E8 or SO32. And they are automatically consistent, right? So that's an example of somehow the modular invariance of the internal CFT translates to the consistency of the space-time theory. And I'm asking whether that kind of thing happens in other dimensions too. Yeah.
Sorry, Yuji, I know the subject very poorly and you might come to this, but are there analogs of Witten's SU2 anomaly in, say, 6 dimensions as well?
Yes, there can be non-trivial global anomalies in various dimensions, and recent progress about anomalies, which you might have heard about, is that in the last few years, we learned a general method to classify all possible anomalies. So before that, say around 10 years, until around 10 years ago, we only knew how to treat global anomalies one by one, right? Mm-hmm. So we could show that this particular global anomaly is absent, and we could show that this another anomaly was absent, but we always had the uneasy feeling that one day you might find another global anomaly which might ruin our fund, right? But thanks to the developments coming from the condensed matter physics side in the last 5 years or so, we learned how to classify all possible anomalies in the first place. And then you can analyze whether the particular theory you are talking about has an anomaly or not. So combining the two in any dimensions with any symmetry structure, at least there is a algorithmic framework to check whether the global anomaly is absent or not.
Okay.
Yeah.
So this is group cohomological approach?
Yeah. So group cohomology was originally advocated by Wen, but they upgraded the understanding. So we now need to use something called cobordisms. Yeah. So it's technical, but it's doable, but it's algorithmic. Yeah.
I see. Okay. Thank you.
Sorry, Yuji. You at some point you had this formula with a -1 to the power n2 minus n6 plus n10.
Right.
You said it, but I missed it. What was n2? What was n6? What was n10?
Sorry, that's the number. Nk is the number of a k-dimensional irreducible representation of SU2.
I see.
So it's just a generalization of the concept of odd number of doublets.
Okay. Thank you.
Yeah.
And sorry, one more question. This anomaly in spacetime, the spacetime SU2 gauge symmetry, could it in principle happen, even though the chiral, the Weissman-Witten algebra on the worldsheet is completely fine, right?
Right, yeah. So I'm going to discuss the anomaly on the space-time theory in the heterotic strings. So I assume that the consistency of the worldsheet theory is already checked. So that's my take.
Yeah, and these could happen together because the worldsheet is just tree level and the space-time is sort of
right. Yeah.
Okay, thank you.
You're welcome. Okay, so that's the end of the introduction. Sorry. So as I said, the question of the absence of Witten's anomaly in 4 dimensions is this purely 2D CFT question, right? And I'm going to advocate this funny math concept TMF, but I believe there should be a more standard approach to answer this question. So I just want some of you to come up with this one, because I'm not really satisfied by the way I'm going to solve this question, because it's really kind of cheating, as you will see.
Sorry, Yuji. I mean, this would be, if there is a CFT, that would be an issue with this background only, or I didn't quite understand it, or is it with the full string theory? I mean, from string field theoretic point of view, doesn't it mean that if you just find one counterexample, one example where this fails, then you are in trouble?
That's a good question. I don't really know. So the question is whether you can move from one internal space-time to the other internal space-time. But I would guess that in string theory, there's some non-perturbative process where you can go from one internal CFT to some other internal CFT. So if some corner is inconsistent, I'm afraid that there's a possibility that there are inconsistencies in the full string theory. Yeah. Okay. So let me come to the main part of the talk. So let me start with some refresher about the standard anomaly cancellation, because I'm going to talk about global anomaly cancellation. I think we should remind ourselves the standard perturbative anomaly cancellation, right? So it's just a standard reminder. So superstring theory, as we know it, started with Green and Schwartz in 1984. So in 10D supergravity with n equals 1 supersymmetry, you can compute the anomaly polynomial of the fermions. And when G is the gauge group is SO32 or E8 times E8, famously, the anomaly polynomial I12 factorizes as a product of degree 4 and degree 8 part. And degree 4 part is trace R squared minus trace F squared. And I put all non-trivial coefficients into the normalization of trace. So I don't want to make the slides cumbersome. So what you do to cancel this fermion anomaly is to say that there's a B field, as we know, and H is the gauge field strength. But the H is not only just dB, but it has a Chern-Simons term from the space-time curvature and Chern-Simons term for the gauge curvature. So that if you take the further d of H, dH is not 0, but dH is exactly this anomaly 4 form I4, which is trace R squared minus trace F squared, right? So one important issue is that because of this mixture of Chern-Simons terms, the B field not only transforms under the standard B field gauge transformation, but it also transforms under the Diffeo and also the gauge transformation. That's the important part. And we further introduce another contribution in the interaction. So in the 10-dimensional spacetime, we assume that there's an interaction of the form B wedge I8, where I8 is the anomaly, 8 form. And because B is not in its, B has a gauge transformation, B has a transformation under the gauge and Diffeo transformation. This combination produces an anomaly, which is exactly DH times I8, which is minus I4 times I8. So the B field anomaly cancels the fermion anomaly, right? So that's how Green-Schwartz cancellation works. The explicit form of I8 is complicated. So let's look at Polchinski. So this is the copy of my, scan of my copy of Polchinski, right? And this is the copy from the newer version of Polchinski. So you see that two equations are rather different, right? I mean, what multiplies n minus 496 is totally different. So I just wanted you to warn that if you work in this type of business, you cannot trust what the famous textbooks say. There are tons of typos, and you need to work out the coefficients very carefully by yourself to really reassure myself that it actually works. So I don't remember exactly when I first checked the anomaly cancellation in 10 dimensions. I must confess that I didn't check it while I was in graduate school. But at some point when I was a postdoc, I decided to do the check, and it was really satisfying, and it gave me a lot of satisfaction when everything worked out right, and I mean, anomaly cancels in 10 dimensions, right? So that's nice. Anyway, so perturbative anomaly, yes.
Sorry, can I ask a question? So
yes.
you said this term B wedge IX8 or whatever you called it.
Right.
You sort of, we assume it's there, or we posit such a term, but it is there, right? I mean, we can.
Yes. So it's automatically generated by the one loop diagram. Yes. Thank you for pointing that. Yes. So both the modification of the B gauge transformation and the B wedge I8 interactions are automatic in string theory. So string theory is automatically consistent in. Yeah. Thank you. So perturbative anomaly is cancelled in 10D, right? Therefore, it's automatically cancelled in any geometric compactification, because if the internal manifold is geometric, then independent of whether the uncompactified dimension is 4 dimensions or 10 dimensions, I mean, you can consider the entirety as the 10-dimensional spacetime and apply the cancellation there. So in some sense, in most of the compactifications, anomaly is automatically cancelled. But the issue is that the internal CFT can be purely non-geometric, right? So for example, in geometric compactifications to 2D, we can at most have n equals 8 supersymmetry. But there are various strange asymmetric orbifolds which give you more supersymmetry than that. So string theory definitely has a corner where the internal manifold is not spacetime, not a semi-classical spacetime. So the global anomaly I'd like to study is in those cases where the internal manifold is not really semi-classically spacetime. So you can ask the following question: is perturbative anomaly automatically cancelled even in the case when the internal manifold is given as a pure CFT without any reference to the semi-classical spacetime? And the answer is yes. There's a very nice paper by here, Nielsen, Skelekens, and Warner, where they computed exactly this B-field coupling Sunil mentioned using worldsheet integral, and showed that it nicely cancels the Fermion anomaly. It's a very nice derivation, but I don't have time to review that. But I just wanted to tell you that the perturbative anomaly is all cancelled. So what about the global anomalies? In 10-dimensional case with E8 times E8 gauge group, the global anomaly was also computed by Witten in 1986. So it uses a sophisticated computation of cobordisms. But in any case, because anomaly cancels in 10 dimensions, it automatically cancels in all lower dimensions if the internal manifold is semi-classically ordinary spacetime. But again, there can be non-geometric compactifications where the gauge symmetry or charged fermions can arise from stringy mechanism. So I just want to ask whether the anomaly is always cancelled in those cases. So I'd like to study them, but it's a bit tricky because of the Green-Schwarz mechanism, right? As I said, D-Fair and gauge transformation are mixed with B-field transformation. And if we want to work in these generalities, you need to always deal with 3 objects: B-field, metric, and gauge field. And that's confusing and complicated. So for the rest of the talk, I'd like to discuss the case where there's no gauge field. So I just want to deal with the B field and metric, right? Which is always there in the case of a heterotic string. So it makes the analysis slightly easier, but because of that, I cannot analyze the original question of Witten's SU2 anomaly, right? So sorry for starting the talk by a question which I do not answer in the end of the talk, but that's how it's organized. I'm sorry about that. So let's talk about the particular global anomaly I'm going to discuss in 2D. So I'm going to consider heterotic compactification down to 2 dimensions. This is very confusing because there are two-dimensional objects, right? One is the 2-dimensional worldsheet theory. Another is the 2-dimensional spacetime theory. So please distinguish them mentally in your head. So the worldsheet theory, which is 2 dimensions, consists of super ghosts, as always, and then the non-compact part of the bosons and fermions, which have these contribution to the CR and CR. And therefore, the internal CFT can be an arbitrary 0,1 CFT with CL being 24 and CR being 12. So that's right. Let's compute how many massless fermions are there in this compactification. Again, you look up standard textbooks, and to count massless fermions, all you have to do is to consider right movers as before, and spin 1/2 fermions come from states with L0 bar being 1, 0, and gravitinos, massless gravitinos come from the vacuum states, right? And again, the space-time chirality is correlated with the worldsheet fermion number, thanks to the Green-Schwarz, Gugliotti-Shirk-Olive projection. So that's the standard statement. So the total fermion anomaly polynomial is given as follows. So spin 1/2 fermion in 2 dimensions is known to have a certain trace R squared anomaly. And I use this Pontryagin class, and this is P1/48. So this is the contribution. Gravitino contributes 24 times, sorry, minus 24 times that of the ordinary fermion. So this is the anomaly of the spacetime theory, right? So this can be non-zero, which makes the theory inconsistent without the B-field coupling, right? So how to compute this number, which can be done by considering the elliptic genus of the internal CFT. So the elliptic genus is Witten index on the supersymmetric side, right? So it has this expansion Q to -1 and constant part, and the leading part counts the gravitinos, and the constant part counts the spin 1/2 fermion. It's all standard. So, and because of this weight factor of the fermion number, A and B actually gives the net chiral contributions to the number of gravitinos and spin 1/2 fermions in 2 dimensions. So this part is given by A and this part is given by B, where A and B are the first 2 coefficients of the elliptic genus of the 2D CFT. Now, as Sunil mentioned, string 1-loop perturbation theory automatically generates the B-field 1-point function in this particular 2-dimensional compactification. And that's given by a worldsheet 1-loop integral, which is an integral over the fundamental domain of SF2Z, as you know. And of course, you need to introduce lots of complicated vertex operators, and there are a lot of cancellations. And at the end of the day, things become just the integral of the elliptic genus over the fundamental domain with this particular factor, which gives this contribution being minus A plus B over 24. So this computation was done 25 years ago by Vafa, Witten, and Ashoksen. So that's a classic computation. So let me summarize. Elliptic genus has this form, A Q to inverse plus B, Fermi anomaly is minus 24A plus B because A is the number of gravitinos, B is the number of fermions, and the B field 1-point function is just minus A plus B over 24. And because B field has a non-trivial transformation under the differential, meaning that DH is P1 over 2, this coupling produces the anomaly, which is this factor times P1 over 2. And that's exactly cancels the Fermi anomaly, right? So the perturbative anomaly is canceled, which is known from 25 years ago, right? But there is one remaining global anomaly because this B field coupling can be a problem when B is not a multiple of 24, right? Because B field is a periodic variable, and the integral of B over the entire two-dimensional spacetime can be shifted. We should be able to shift that by +1 without changing the physics. But when B is not the multiple of 24, this B field coupling can produce some 24th root of unity. So there can be an anomaly if B is not divisible by 24. So it's a very subtle global anomaly. And I'd like to ask the following question. So let's take an n equals 0, 1 SCFT with CL and CR being 24, 12, right? Which can be used as the internal CFT for heterotic compactification down to 2 dimensions. Let's say its elliptic genus has this expansion AQ inverse plus B plus . The question is whether B is divisible by 24. It's a weird question, right? You don't usually ask whether the number of states is divisible by some strange integer like 24. Again, I don't know how to approach this question in any standard manner. But at least you can go over examples, right? So, yes, please.
Sorry, this Z24, is it related to modular anomaly of the spacetime theory?
Yes, it's exactly the modular anomaly you get by doing the T transformation in the space.
Yeah.
So you can compactify the yet to be uncompactified two-dimensional part into T2 and perform the T transformation. Okay. And this Z24 is exactly the phase you get. Yeah, but because we are supposed to sum over entire space-time geometry in string theory, we should be able to do that, right? But if B is not divisible by 24, you run into a problem and string theory just becomes inconsistent. Yeah. So I think this is a very nice question we can give to anybody who hates string theory. So it doesn't refer to string theory in itself. So you can study it as is, and if you find a counterexample, then string theory is doomed. So that's how it goes.
So the divisibility of B by 24 that can arrive both in geometric and non-geometric compactifications. Is that right?
So in geometric compactification, it is always a multiple of 24. You can show that.
Okay.
Because in 10 dimensions, it's already guaranteed that there's no global anomaly. So even after compactification, you can regard the entire spacetime as still 10 dimensions, right? Even when you compactify. So the global anomaly goes away.
Okay.
Yeah. So I'd like to show that the divisibility of B by 24 can be shown using topological modular forms. But before talking about topological modular forms, I'd like to remind you about modular forms. Right.
Sorry, Yuji, this geometric compactification, as you said, it can be thought of as just the 10-dimensional space, but compactified.
That's right.
But for global anomalies, wouldn't different topological things be classifying these things depending on what kind of manifold you're on? I mean, different homotopy groups and so on.
Right.
So I guess, as you said, the cobordism, etc., would be very that's the way it would be done, right?
That's right.
And
That's
then
right.
is it always straightforward that this is how it works? That you don't get, there is no possibility of any other anomaly depending on which manifold you work on.
Right. So surprising thing is that Witten in his paper in 1986 already realized that you can just study cobordism group to show that global anomaly just vanishes due to the vanishing of the cobordism group itself. So yeah.
But then there are these die-freed anomalies. So your statement applies to all these things.
That's right. That's right. Yeah. So once you understand the framework well enough, then even before computing the possibility of anomaly in 10 dimensions, you can convince yourself that in 10 dimensions, you just cannot write an anomalous term. Yeah. So always in the analysis of symmetries, what you do is to classify all possible terms you can write under various consistency conditions, and you check whether that term actually arises, right? But in 10 dimensions, you cannot even write an anomalous term. So,
but global anomalies would go slightly differently, right? Or I mean, because okay, I don't remember these things, but I vaguely remember from Witten's paper that it's the eta invariant and so on, right? So it's is it one higher? Okay, I'm sorry, I'm not remembering these things, but would the treatment be very similar to the perturbative anomalies, or?
Yes. So once you use the proper language of eta invariants and the Bordism group, the analysis of the perturbative and global anomalies are in fact unified. And then in 11 dimensions or in 10 dimensions, what you do is that you realize the anomaly of 10-dimensional theory as the boundary effect of the 11-dimensional bulk anomaly theory.
Yes.
And the general argument using cobordism shows you that you just cannot write any non-trivial anomaly theory in 11 dimensions.
Okay.
So you just cannot do anything wrong with 10 dimensions.
Okay, thank you.
Yeah.
I see. But sorry, and you should go on because I really don't understand the subject well. But if you think of the heterotic then as the 10D boundary, sometimes you can get anomalous theories on boundaries, right?
Yeah, that's right. But in 10 dimensions, you just don't have any anomalous theories. That's the funny part.
I see.
I mean, perturbative anomaly can arise in 10 dimensions, and that's guaranteed to cancel thanks to Green and Schwartz computation. Then the next step is to analyze the global anomaly, but a general analysis tells you that there's just no possible global anomaly in 10 dimensions. So as long as the internal manifold, internal CFT is geometric, then global anomaly cannot arise.
I see.
And in fact, you can use standard differential form computation to show that B is 20 multiple of 24. That's the strange fact.
Thank you.
Sorry, one stupid question. The internal CFT can be a product of geometric and non-geometric part, right?
Right.
It's not entirely non-geometric. It can be a product of geometric.
Yeah. Right.
Nice.
So once there's a mixture of non-geometric CFTs, then the problem arises.
Okay, thanks.
You're welcome. All right. So let me remind you the modular forms. So let's forget about the constraint on CL and CR for a moment and consider a general two-dimensional 0,1 theory, right? And you can always compute the elliptic genus, which is just the Witten index applied to the supersymmetric side. So all you remain is the excitation in the non-supersymmetric side, right? So this is a partition function of the theory on T2 with periodic spin structure. So the periodic spin structure on the spatial side corresponds to the R sector, and the periodic spin structure on the temporal side corresponds to the insertion of the fermion number, right? So people often say that because of that, elliptic genus is modular invariant, but that's not perfectly true. There's a subtle phase, which is the 24th root of unity, which Abhijit already mentioned, right? in the case of spacetime theory. But in the case of worldsheet theory too, because of the T transformation, you can have a non-trivial phase. But that's determined by the gravitational anomaly. And that's determined completely by just the difference of CR and CL. So twice CR and C minus CL is denoted by nu in this talk. And to cancel the global anomaly, sorry, this T transformation anomaly, let's add new left-moving fermions, right? Formally to cancel the anomaly, to cancel this annoying worldsheet anomaly. But if you do that, total elliptic genus is 0, right? Because of fermion zero modes in the periodic sector. So it's 0, nothing interesting. So you need to add new fermion operator to absorb the 0 modes. Then you get this combination. So eta q to the new power nu times the original elliptic genus, where eta is the Dedekind theta. So this is the partition function of the free fermion on the periodic torus, but with the 0 mode removed. So this combination is known as Witten genus by mathematicians from some historical reasons. And thanks to the anomaly canceling fermions, there are no anomalous phases. But because we inserted fermion 0 modes, you have an additional non-trivial transformation of this form, which comes just from the transformation of the eta, Dedekind theta. So the price we paid is that Witten genus is not the modular invariant function, but it's a modular form of weight nu over 2. So modular form of weight W is a function over the upper half plane with this transformation law.
Sorry, Yuji, what was nu? Was CL minus CR? Something?
Yes, twice
That's a fixed number, right?
CR.
So that's a fixed number in this case, right? Which is 24.
Yeah.
Okay.
Yes, it is 24. So in this particular case of two-dimensional compactifications, you don't have to introduce this factor to make it non-anomalous, but yeah. But to analyze arbitrary compactification down to arbitrary dimensions, you need to, it's better to consider general situation. So mathematicians, when they talk about modular forms, they define it with the condition that it becomes smooth, it becomes finite when Q goes to 0, right? Then the modular forms is known to be generated by Eisenstein series of degree 4 and 6. Eisenstein series is just this, which is clearly modular covariant with some factor. But we physicists need to allow poles in Q. So to provide poles, you need to use this modular discriminant, which is a 24th power of eta Dedekind theta, which starts with Q plus dot dot dot, right? So you can always cancel the poles by multiplying by a certain powers of delta. So conversely, any modular forms allowing poles at Q equals 0 is a polynomial ring over E4, E6, and delta inverted. So you allow inverse delta. And we also know that Q expansion of the Witten genus is always has integer coefficients, right? It comes from the Hilbert space dimensions. So the expansion coefficients are integers. And the mathematicians are clever in that they know exactly what are the possible modular forms with integer coefficients. They are generated by normalized Eisenstein series. So standard Eisenstein series have pi's and Bernoulli numbers, blah, blah, but you can multiply them to remove it so that it starts with 1. Then all of the coefficients are integers. So basically modular forms with integer coefficients are generated by normalized E4 and E6, but then delta, Dedekind theta to the 24th is a linear combination, but only a rational linear combination. So you need to introduce delta and with this additional constraint. So it's a technical comment. And finally, for our purposes, we need to allow poles. So you need to also allow inverse of the discriminant. So the modular forms with integer coefficients and poles of this object, right? So does this mathematical consideration buy us anything? Can we answer this question whether B is a multiple of 24? Unfortunately not, because, you know, in our case, nu is a particular number, minus 24. So written genus is eta to minus 24 times the elliptic genus, which is just the Dedekind modular invariant minus 1, modular discriminant to the inverse times A plus B, right? So this is a modular form of weight minus 12 with intercoefficients and poles. So the only possible basis term you can use is Eisenstein series, the cube, divided by delta minus 2, or delta inverse itself. So modular invariance and degree consideration constrains it to a linear combination of just two terms with integer coefficients. So that's nice, but we know that A is, but this only tells us that A is integer and minus 7448 plus B is integer, but 744 is a multiple of 24, so it doesn't tell us anything. So it just tells us A and B are integers. It tells us that A and B determines all the rest, right? All the rest of the spectrum, but it doesn't give us any clue about the divisibility of B. So finally, I'm coming to the topological modular forms.
Sorry, Yuji, may I ask you a question, please?
Please.
In the previous slide,
Yep.
in the written genus, why is there no term of the form C6 square delta minus 2? Because I thought it should be a natural allowance in the ring of...
Because of this relation, C4 to the cube minus C6 to the square is 1728.
Oh, okay,
delta.
you just take that. Okay, I see.
Yeah, so you can rewrite this in terms of C4 to the third.
Okay, I see.
Yeah.
Thank you.
You're welcome. You are following the slides very closely. I really admire that. So topological modular forms. So it has a nice acronym TMF. It's the topological version of modular forms. It's something distantly inspired by Witten's work on elliptic genus in 1986. So it was mathematicians who introduced the word elliptic genus. And then Witten wrote in that paper in 86 saying that mathematicians' elliptic genus is the Witten index of a two-dimensional supersymmetric theory. So that's what he said in his paper. And we physicists only took that statement and we just call the Witten index of two-dimensional supersymmetric theory as elliptic genus without knowing anything about what mathematicians mean by the word elliptic genus, right? But that's the situation. But mathematicians continue to study their elliptic genus for a long time. And around 2000, using algebraic topology and algebraic geometry, some combination of them, TMF was born. So that's done by Hopkins and collaborators. The exact method they used is far above my head. I tried to learn, but it's very hard. So this is the textbook I'm trying to read. It seems readable, but I have this book for about a year, but progress is slow. For us, Segal-Stolz-Teichner conjecture helps. So TMF nu is some abelian group, but these mathematicians proposed the following. It's the equivalence class of two-dimensional 0,1 supersymmetric theory with this particular nu, which is the difference of the chiral central charge multiplied by 2. And you identify two supersymmetric theories when they can be continuously deformed to each other, right? So they say that the classification here gives you this mathematically well-defined object TMF.
So just you're quotienting by flows due to marginal operators, basically.
Not just marginal operators. You need to allow all relevant and irrelevant. And all
I see.
possible.
It's bigger. I see.
Yeah, so that's how you get a very rough classification. Yeah.
I see. Okay. Thank you.
But in particular, I mean, elliptic genus of a theory is an invariant under such deformation, right? Elliptic genus is a written index, so it's always invariant, even under the relevant or irrelevant deformation. So that's the interesting part. So that's a very crude classification.
I see.
Wait, Yuji, I mean, elliptic genus under RG flow, would have some rearrangement of R charges because the conformal symmetry, new conformal symmetry and so on. So doesn't that make, it different a little bit at least?
So you need to assume that the spectrum is discrete. Yeah. So if you have continuous part, you can have a non-trivial change under RG flow, but assuming that the spectrum is discrete, then the standard written index argument guarantees that the elliptic genus is invariant. So thank you for raising the point. So mathematically, there is a map from TMF nu to modular forms with integer coefficients and poles of a particular weight. So that corresponds under this conjecture to the written genus, right? So if we assume the validity of this conjecture, then given an object in TMF nu, there should be a two-dimensional theory realizing that. Then you can compute its elliptic genus and multiply by some power of dedicated eta, and we should get some modular form of integer coefficients and poles, right? That part we can understand. But the good thing is the mathematicians computed exactly a map with that property. And what's strange about that is that mathematicians are sophisticated enough to compute exactly the image of this map. So it is not a surjective map. It has a lot of empty slots in. So as I said, I mean, the element is always of the form C4 to some power, C6 to some power, divided or multiplied by some power of delta. And because of this property, you can choose I to be non-negative, J to be 0 or 1. Otherwise, you can always use this property to relate in terms of C4 and delta, and K is an arbitrary integer, right? So this thing, modular form with integer coefficients and poles, are generated by all integer monomials of this form, right? But mathematicians say that the image of the written genus is either is given by this particular thing, right? So it says that whenever there's a factor of C6 here, the coefficient needs to be even, right? And the most important part is this first line. When this factor and this factor is absent, so when I and j are 0, it's just a pure power of delta, right? So when the written genus is a pure power of delta, then the coefficient is 24 divided by GCD of 24 and k. This is a weird relation, right? But let's assume that. So assuming this conjecture, we know exactly which modular function appears as the elliptic genus of 2D supersymmetric series.
Sorry, Yuji, I didn't quite understand this conjecture. So where is this coming from? I mean, this conjecture, the way you phrased it is said that there's some, this TMF comes from some 0,1 theories identified with continuous deformations and so on, right?
Right.
And mathematicians are telling us that 0,1 theories up to continuous deformation should look like this.
That's right. Yeah, I have zero idea how they come up with that, but but there are many indications why this is the case.
No, but they don't know what 0,1 theories are. I mean,
that's the strange part.
So what is it? So there's something else going on. I'm asking, what is it that is going
on? So they have a purely mathematical definition of TMF, but but that's very technical even to them. So they want some more understandable definition, and they tried very hard, but the only thing they could come up with is this statement in terms of 2D CFT. Yeah.
The previous statement that we obtained was with this kind of understanding that 0,1 theories, should their elliptic genus should transform in certain ways. That's why you reached this basic definition. Now,
Right.
now you are allowing, so the additional point is that you are allowing some marginal, relevant deformations, etc. And that is what kind of reduces the space down to this one.
Right. Yeah, it's hard to say. I mean, I'm trying to give you some motivation to how mathematicians came up with this conjecture later. Well, I already used up all of my time, but yeah, let me try that. But let me first show you how that B is a multiple of 24, right?
Okay.
So assuming this mathematical statement, we know exactly which modular function appears as elliptic genus of 2D theories, right? So we can show that this B is multiple of 24, right? So this is the elliptic genus, right? But this should be in the image of this particular map mathematicians constructed. So as I already said that Witten genus is linear combination of C4 cubed divided by delta squared or just delta inverse, right? It's this coefficient. But we use this mathematical theorem that this is delta to the power -1. Therefore, K is -1, right? So GCD of 24 and 1 is 1. So 24 divided by 1 is 24. Therefore, the coefficient here needs to be a multiple of 24, right? So it's divisible by 24. We are done. So that's the power of TMF. So that's the main part of the talk. And let me try to summarize. Of course, we are not done, right? I'm puzzled as hell. So what I did was to transfer the question of global anomalies of heterotic strings into the validity of Segal-Stolz-Teichner conjecture, right? So what's going on? I mean, how did they come up with this conjecture? Why should we take this as, yes, please.
Sorry, so I should think of this conjecture as something that imposes constraints on elliptic genuses?
Yeah, that's right.
So there are some properties of elliptic genuses that have not been proved but have been conjectured.
That's right. So in the rest of my talk, I'm trying to give you some examples what this mathematical conjecture tells us about what to prove, right? What to show about 2D CFT. So it's interesting, right?
Sorry, Yuji, one more comment. So,
yes,
so
please.
the implication of this discussion, not just that B is divisible by 24, but A should be 1 also. That also is somehow following from here, right?
Not really. I mean, A can be big because it's not just a number of vacua, because it's a Witten index. So it's
can you go back to that slide where you argued, yeah, this one. So here A is a coefficient of C4 cube delta to the -2, and in this table here it says otherwise it should be 1. It says.
Yeah. So it's a multiple of 1. So it can be any integer.
Oh, multiple of 1.
Yeah, that's right. It's an integral linear combination of these basis elements.
I see. Thank you.
Yeah, you're welcome. So 2 questions immediately arise, right? Assuming the conjecture, what can we say, right? And also, how about the conjecture itself? So we can raise 2 questions. So assuming the conjecture, what can we say? So today I will only discuss this 2D anomaly, which is Z24. How about the original 4D SU2 anomaly, right? How can we study that? Well, so the original question was that, right? You pick a particular choice of chiral central charge suitable for the 4D compactification. And what about the Witten index? I mean, Witten anomaly. So such a CFT determines a class, again, in TMF group, but with argument BSU2, whatever that is. I'm not going to explain the details. So the question of 4D Witten anomaly can be reduced to the study of a certain topological modular form computation. Unfortunately, this is very complicated. I didn't find anybody who would compute this for me. I tried many mathematician friends of mine, but nobody was willing enough to compute it for me. Yeah, you can. So what I wanted to say in this slide is that in any space-time dimension and any gauge group, you can rewrite the question into the question about TMF. So heterotic anomaly question can be always translated into TMF question, but the TMF question is very hard to compute.
Sorry, what is B in this notation, please? G is the group. What is B?
B is the classifying space. Yeah, sorry about that.
What does that mean, sir? That's not the big.
Yeah, you can forget about it.
Okay.
Yeah, so there's a standard machinery to convert anomaly questions into algebraic topology questions. And in those questions, you usually don't use the group manifold itself, but something called classifying space. Yeah. But the detail doesn't matter. I just wanted to say that heterotic anomaly computations can be always transferred to the question about algebraic topology, about TMF. And
Yuji, sorry, just to get at least a glimmer. So in any number of or at least in whatever even dimensions, etc., the TMF is maps to an equivalence class, is it, of field theories quotiented by continuous deformation?
that's right. That's right.
Is it? I see. And
that's
then
the conjecture.
I see. And then can you give us, sorry, very layman kind of intuition for what is it that allows them to come up with something so specific?
Let me try. I'm coming to that.
Okay.
So let me finish this slide.
Yeah.
So just one question. The K, does
yes,
that
please.
refer to the level of the Wessel-Witten algebra?
That's right. K is the level of Wessel-Witten.
So if this conjecture is correct, is it correct for only for those deformations that preserve this GK structure?
That's right. That's right. Yeah.
So that in particular preserves conformal invariance then?
No, you don't impose conformal invariance. No.
But what does GK mean? I thought GK was a current algebra kind of structure, which
Well, G is just the structure of the. Sorry, G is just a symmetry group, right?
Yes.
K is the anomaly.
So more general. Thank you.
Right. So it's more general than just CFT. So the point of this part is that instead of attacking questions about individual D and individual G and individual K one by one, a mathematician friend of mine found a general way to show the vanishing of the anomaly for arbitrary D and arbitrary G and arbitrary K at the same time. Yeah, so it's a work in progress, but I just want to announce here that we can show that heterotic global anomalies always vanishes. Yeah, so we are still writing the paper, but it should eventually appear. But I guess more interesting question is how the conjecture itself, right? So TMF is supposed to be this, but there are surprisingly few mathematical papers about it either, because for mathematicians, I mean, we often hear Nati Zeiberg's lectures saying that QFT is not well defined and still to be defined, blah, blah, even for us, right? So for mathematicians, this is totally ill-defined. So they also think about it, but they cannot write papers about it. So there are very, very few papers about it. But the left-hand side was defined by mathematicians rigorously by totally different means. And if you assume that, you can conjecture many subtle properties of 2D CFT, right? So for example, TMF group is periodic with period 576, which is 24 squared. So it says that this classification of supersymmetric theories in 2 dimensions seems to be periodic if you increase the difference of the chiral central charge by 288. Why? I mean, it's mysterious. Another example is this. TMF3 is known to be Z24. This means that if you try to classify 0,1 theories with 2 times CR minus CL being 3, is Z24, right? And each class in K, I mean, mod 24 is believed to be given by just 0,1 sigma model on S3, group manifold of SU2, with Wessel-Witten level K, right? So each of them has different central charge, but the difference of the left moving and right moving central charge are always given by this. And Gayotto, Johnson, Freid, and Witten studied how to see model 20 behavior in this class of examples. And also Gayotto and Johnson, Freid have a paper, how to extract Z24 invariant for using the subtle property, modular property of the partition function. So mathematician says this, right? From totally strange regions, which we don't understand. But you can come up with field theoretical arguments saying that if you classify this class of theories, you get Z24. So that's one.
Sorry,
right?
Yuji?
Yeah.
One question. So sorry, can you go to the previous slide?
Yes.
Yeah, here the mod 24 behavior means that the elliptic genus is going to be, so the SU2 WZW model at level K and K plus 24, the elliptic genus of the two are going to be related in some way?
That would be nice, but unfortunately, the elliptic genus is also 0.
Okay.
Yeah, but you can consider a more subtle version of elliptic genus, which only makes sense modulo 24. And you can, yeah, that's exactly what these two papers did. Yeah, so they are marvelous papers in 2D field theory analysis. So they extracted some Z24 invariant, and that turns out to be K modulo 24. Yeah.
Yes.
Yeah.
And CL minus CR is independent of K because K cancels from CR, right?
Yeah, right. K, yeah, it's a gravitational anomaly, so it cannot change.
Yeah.
It's just determined by the fact that it's geometric in the large radius limit.
Yeah.
Can I ask a question?
Yes, please.
Can I go to the previous slide? Yeah, so here there is a global symmetry of the SU2 with
That's right.
But the Z24 classification does not care about the global symmetry, right?
That's right.
So what's the so we consider the SU2 left hand, the SU2 right global symmetry. What TMF can tell us?
Yeah, so in that case, we need to compute TMF3 with BSU2, right? With K level something, and that gives you more refined data. Yeah, I don't know how to compute them, and I don't know whether people have computed them, but that would definitely tell you about the classification of two-dimensional CFTs with SU2 symmetry. But here we allow deformations which do not preserve SU2 symmetry, and that reduces the classification down to the Z24. Yeah, if you preserve SU2 symmetry, then definitely level K is an invariant which you cannot change because it's an anomaly.
I see. Thank you.
Sorry, one more question. So you said TMF is a group, right, or a ring?
Right.
So not a ring then.
TMF is a ring, but the ring operation, the multiplication multiplies, adds this index nu.
Okay.
So the ring operation, multiplication operation in 2D language, 2D CFT language is just to take two theories and multiply it. Okay. The addition is just to consider direct sum of theory.
But if you allow for that, then it's a ring. So,
yeah.
Okay.
So also I said that we know, if we assume this map is the elliptic genus map, we know exactly which elliptic genus is possible, right? So in particular, let's concentrate on this most strange behavior, right? So one consequence in our language is as follows. So consider a 2D theory with twice CR minus CL is 24K, right? Then suppose elliptic genus is constant. suppose every Q dependent part cancels, right? When you compute the elliptic genus and you just get constant, then it is a multiple of 24 divided by GCD 24 by K. So this is a strange statement, but Gayotto and Johnson-Frade constructed example when K is 1 to 5. So it's a very weird statement, right? So when K is 24, for example, so which corresponds to CL minus CR equal 288, this mathematical conjecture tells us that that's definitely a 2D 0,1 SCFT whose elliptic genus is just 1, a constant, right? Conversely, this conjecture also says that if the elliptic genus is simply 1, then CL minus CR is divisible by 288. It's a very weird statement, and I just don't know how to tackle this. So,
sorry, Yuji, how is the second statement coming about that there should be a theory with such property? I thought it would be like the first statement that would follow, but how is it telling us about existence?
Because mathematicians, if we assume the conjecture, what mathematicians have showed that the image is exactly this. So image of this elliptic genus map is not just within this subspace, but exactly this subspace. That's what mathematicians showed. Yeah.
So everything is realized.
That's right. That's part of the statement. So constructing such a CFT is a fun project for any student of 2D CFT, right? This is understandable without understanding the delicacies of TMF, right? So, but I just don't know how to proceed. So today I started my talk by talking about global anomalies in heterotic strings, but eventually I transferred it to the mathematical theory of TMF with the help of the Segal-Stolz-Teichner conjecture. But this conjecture predicts many unexplored properties of 2D theories, which I think are worth pursuing. So thank you very much.
Thank you very much, Yuji, for an exciting talk. Let's all unmute and applaud.
Thank you very much. Any questions?
Could I ask a question? Yeah,
Yes,
Yuji,
please.
that was a beautiful talk. Thank you so much.
Thank you.
I had a couple of one question and one comment. So this property of TMF nu, which you have written, this sort of definition of TMF nu, which is a 0-1 supersymmetric theory over continuous deformation. Obviously, one has, you didn't explain how this really works internally, but one can study that. But I was trying to, I didn't see in all the things you discussed about TMF, it didn't look like, it looked, okay, let me put it another way. It looked like TMF might also have relevance to non-supersymmetric CFT. Is that a possibility? Because it seems to depend on poles of modular forms and so on. And so where does the supersymmetry aspect really operate?
Well, without supersymmetry, I don't think we can construct any invariant. Because you cannot guarantee that the dimension of each level is constant, right? So thanks to, at least you need some kind of written index argument to extract some kind of constancy under the deformation.
So the partial cancellation of supersymmetry is basically this concept. Okay.
That's right. Yeah, without that, it's very difficult to proceed.
And the comment is that, there's been an idea for a long time that maybe this approach of modular linear differential equations can be applied to superconformal field theories.
Right.
And it has been also in a fairly recent paper by the Korean group. But I was thinking that, you gave an example of some theory you want to find out whether it exists with elliptic genus 1 and central charge 288.
Right.
These kind of discrete questions typically are answered well by the MLD method. I mean, often, not always.
Right.
So that was just a suggestion that maybe, if one can formulate this properly for elliptic genus, one might be able to answer these very focused, discrete questions. It's not very good for classifying large families, but it's good for answering specific questions.
Right. I definitely hope so, because this approach using TMF is so, I mean, above my head. I just don't understand how they come up with these predictions. So I would hope there's a more conventional way to us to understand these predictions. So I really love to have a easier understanding of what's going on.
Right.
Yes.
Thanks.
Yuji, can you give us even a vague sense of where these things are coming from, these additional constraints coming from? I mean, what is the additional structure the mathematicians are putting in, or just even a...
So I'm going to, I mean, mathematicians consider objects on the torus. That's definitely true. So they consider elliptic curves, right? But the funny thing is that they consider elliptic curves over characteristic P, which is 2 or 3. So meaning that they consider not just elliptic curves over complex numbers, but they consider elliptic curves over characteristic 2 or 3. So it's like periodic string things.
Oh, finite fields. So this is coming from consistency or finite fields or something.
Yeah. So they consider the behavior of TMF class on the elliptic genus over finite fields. And that gives you funny factors of 2 and 3. Yeah. So we know very well that in over complex numbers, only symmetric elliptic curves are, I mean, this square and this triangle, right? So you only have Z4 and Z6 symmetry, but over characteristic 2 and 3, apparently there are more symmetric elliptic curves, which are called supersingular elliptic curves. And by considering the consistency of the TMF class over them, they could extract additional factors of 2 and 3, which gives you this additional factor of 24. So there are colleagues of ours studying periodic strings, and maybe it might be that these 0,1 supersymmetric theory can be formulated on those places.
But from this point of view, I mean, one is, I guess, saying that there is a yet additional consistency condition that things should make sense over finite fields, and I don't see why should there be such a condition.
So at least that seems to be how mathematicians are approaching TMF and extracting additional factors of 2 and 3. But I should emphasize that the analysis by Gayotto, Johnson, Frade, and Witten, when they get Z24, was not like that. If you read these papers, it's purely standard 2D CFT, 2D field theory analysis over complex numbers or real numbers. So there's no modulo 2 or modulo 3 periodic strings whatsoever. But they arise, they came up with the same answer. So that gives me additional confidence that this mathematical conjecture is telling us something.
Thank you.
You're welcome.
Sorry, Yuji, I'm going to ask what is it? An embarrassing question, but let me ask it. So this TMF, for the mathematician, what is it a function of, and what is it? Is it a number? Is the answer to this TMF a number, a complex number? And what, if so, what is that number a function of?
TMF is a version of cohomology theory. So cohomology theory or K theory gives you an abelian group if it's given space and dimension, right? So if you have a space X and dimension D, you can compute degree D cohomology, HD of X, right? And mathematicians then came up with K theory, K0 or KD of X, right? So mathematicians, after this experience with cohomology group and K theory, they wanted to have a better version. the third step of the progression from H, K, and something. And mathematicians say that TMF exactly this something. There are many indications that exactly this TMF is the second step or the third step in this progression. Yeah.
Okay. Okay. And sorry, and what is it a function? I mean, what are the variables that go into defining this TMF? Right.
TMF is a function of two variables. One is nu, which is an integer. Another is a space. It's exactly as in cohomology, right?
Okay. Okay.
Yeah,
And
so,
please go.
and when I say just TMF3, I'm just taking the space to be a point.
Okay.
Yeah.
Okay. And then in this conjecture relating field theories, modulo RG flows to TMF, nu translates into CL minus CR.
That's right.
And what does the space translate into?
It's a parameter space of CFT. So you can consider family of CFT, right? Parameterized by some external parameter X.
I see. So this abstract space parameterizes different classes of field theories that are related by flows.
That's right. That's right. Yeah.
Okay. So given nu, there is a and this space, you know how to classify these allowed spaces. You know how to label.
Okay. No, it's arbitrary. Yeah.
But it's a geometrical space.
It's a parameter. You can consider. I mean, when we consider field theory, it has lots of parameters, right?
Right.
We usually consider only small variation of these parameters, right?
Right.
But you can also think of the parameter space. Parameters itself forms a space, right?
Yes, I understand.
So you can consider a non-trivial space, and you can consider a bundle of CFT.
Yes.
Continuously parameterized by that space.
Yes.
Then you can try to classify that kind of bundles.
Yes.
That gives you TMF nu of X.
Yes. So I was wondering, so the answer to that class, assuming the conjecture is right, the answer is this is given by two things, by nu and X. And I was trying to understand whether you know what X is, what the possibilities for X are.
No, it's possible. It's an arbitrary space.
Sorry, what is X? Shiraz, this TMF is Yuji, this TMF is a function of Q, right? I mean, this is the Q of the elliptic genus, right?
No, TMF nu, TMF is a function of TF nu, and I didn't write the second argument, but there's a second argument, which is a space, arbitrary space X. In that case, if you compute the elliptic genus, it's a function over X. So it's,
okay. It's all these classes, the things in the denominator here.
Right.
Okay.
So sorry, I just make sure I understand. So the field theories that can be deformed to each other are labeled by nu and X.
That's right.
And for this statement to have content, you have to know over what X can range.
Mm-hmm.
So you know over what X can range. I don't understand what X is. Is it a geometrical space? Is it like set of points? Is it something
it's arbitrary, because you can consider arbitrary. I mean, family of systems are parameterized by arbitrary thing, right?
Okay. So then it's. I mean, let's say that I see. So what is useful about this is that if you have two theories characterized by the same nu and the same X, then you can say they must have the same elliptic genus.
That's right.
That is the content of this.
That's right. That's the content. Yes.
Okay, and therefore, by relating the elliptic genus of some system which you don't know about to the elliptic genus of some system that you do know about, but that does have the same X, you can find new properties of the elliptic genus. Of
that's right. That's
the spirit. Okay, thank you.
That's right. And even just consider the space to be a point.
Yes.
You get various strange statements like this.
I understand. So the point gives you the simplest class of theories.
That's right. Yeah.
Okay, thank you.
There's one raised hand.
Yeah, in the chat. Yeah.
Yes.
Go ahead.
Is there? Do you expect any more restrictions on B, in the sense of the meromorphic CFTs classified by Schelikens, or is it just an arbitrary multiple of 24?
You seem to get arbitrary multiple of 24. Yeah, because here in the TMF class, you need to consider arbitrary integer linear combination of CFTs. while Skedeken's list only considers irreducible two-dimensional CFTs, which is not a direct
Right.
sum.
Oh, I see. I see.
So you get
I
slightly
understand.
different. Yeah.
I see. Understand. Okay. Thank you.
And I'm afraid I need to go.
Okay. Yes.
Yeah, you need to pick up my kids.
So let's thank Yuji again for a wonderful talk.
Thank you very much.
Thank you very much, Yuji. Thanks for giving your first Zoom talk to us.
Yeah, it's a great honor. Thank you for the nice questions too.
Okay.
Bye.
See you.
Thank you.